Good afternoon, everyone. Thanks for spending your afternoon with us. I hope every one of you are enjoying Google Cloud Next. And I'm pleased to see so many people here to learn about our journey in securing multi-tenant service mesh in using GKE. I see a lot of Snap friends here. Thanks for coming. Google partners, thanks for coming. So I think we have a good team over here in case you have a lot of questions at the end. So I'm Shrikant. I'm engineering manager for infrastructure security team at Snap. And we own areas of cloud security posture management and building platform security controls. My team also builds and maintains Beyond Corp authenticating proxy, providing secure access to our workforce to internal infrastructure.
Hey everyone, super excited to be here today. I'm Sagiv Shilo. I'm a security engineer working on infrastructure security at Snap with a focus on our Kubernetes and cloud security controls.
Okay, so what we have all for today. We'll briefly walk through the evolution of Snap's backend platform over the time. We'll cover why certain design decisions were made before and why those decisions led us to considering multi-tenancy. Then we'll talk about how the new design changed our existing security boundary and introduced new security risk. And next, we'll talk about the security controls to mitigate against those risks. And as we all know, every project goes through challenges, and we had ours too. So we'll share some of the organizational as well as technical challenges that we faced. And we'll have time at the end for Q&A, so please be ready with your questions. So to start from the beginning, Snap started on App Engine. It was a great platform to bootstrap an idea and scale quickly to millions of users, sending and receiving snaps. However, over the 5 years into its life, Snap grew with multiple user-facing products as well as dependent backend services. As you all know, monolith architectures have limitations. And we also started facing similar kind of limitations related to either scalability, developer velocity, etc. At the same time, Snap made strategic decision to go multi-cloud. Hence, we wanted to build an abstraction platform that would work on multiple clouds. And this led us to think about service mesh, and we chose Kubernetes to build our service mesh on. So this is a high-level overview of our single-tenant service mesh. This is our existing legacy service mesh, and we'll talk about how we moved from this model to the new multi-tenant service mesh model. Over here, we use open source Envoy at API Gateway, as well as at Sidecar for service deployments. Switchboard is our in-house built service configuration portal that syncs all the control plane artifacts such as service-to-service trust, gateway routes, configurations like transport parameters, etc. And the most important thing to note over here in this diagram is each of these services gets its own GKE cluster, which is managed by respective service teams. Now, some of you who have basically had service mesh kind of platform or use GKE would be wondering why we chose some of these decisions, which is basically a cluster per service. So we made this decision choice to limit the blast radius. When we started designing our service mesh, it was our first time venture into Kubernetes at a very large scale. And given our business need for multi-cloud, there was no feature parity between KTS offerings across multiple cloud providers. However, as the number of services grew, we noticed explosion of clusters that we had to maintain for so many of microservices that we supported on our backend. The second point is about decentralized operations. Earlier, we did not follow SRE model, so we had to rely on, for the cluster management, on the respective service teams. This delayed our upgrades and patching. The next is about non-standardization in CI/CD. So far we mentioned some of the challenges within the production environment or within the service mesh platform. But for the part towards the production or the service mesh, we didn't have a strong story around it because we could not enforce any golden path for CI/CD. And this made This made the rollout to the service mesh or the rollout of services challenging, and developers had to spend a lot of time understanding how their services are doing. The tooling that we had to build was challenging itself. And this made us to think about the mesh that we need a little bit better. And while we were rethinking mesh, we also took this opportunity to improve some of the security posture within our mesh. We had broad IAM access for services, and our operators had unrestricted access to production. And as you all might know, this kind of has not only security problems, but even production's integrity and sanctity can be a problem. The deployments lacked provenance, and our production lacked integrity against unknown compromises. The vulnerability responses lacked unified tooling. And the heterogeneity of the fleet made it expensive for our DNR team to roll out runtime monitoring. And we have some of our DNR folks here, so if you have questions, we can always discuss. So the limitations we discussed about our single-tenant service mesh led us to start thinking about optimizing our service mesh with multi-tenancy. So just to set or establish shared understanding for the terms that we are going to use today, when I say single tenant, I mean a cluster per service. And for multi-tenancy, we are running multiple services within GKE cluster. Now, all of these services are owned by the teams at Snap. However, we call those different tenancy, or basically we started thinking about tenancy model because each of these services have their own different threat model. They have different permission model. They even have different cost model, basically attributing cost to each of those services. And if we have to optimize them in a shared environments, we also had to think about how does the security requirements change or the boundaries change. So how did we build a multi-tenant platform? So the objectives we put forth were to abstract the infrastructure and standardize developer experience. And the tenets that we wanted to force ourselves on were, first thing, opinionated platform that enforces best practices. Earlier version of our mesh there was not much of opinionated enforcements over there. So that kind of led to a lot of heterogeneity within our platform, and we wanted to move away from that. We wanted to have centralized infrastructure management that will help us basically upgrade on our fleet. The whole entire fleet management would be easier, and we can automate it end to end. And also, the most important thing, as we scale fast, as Snap grows fast, we wanted to have high velocity for infrastructure changes. Now, I will hand it over to Sagiv, who will take us through deep dive on the security risk and mitigating controls. Sagiv is tech lead on our team and a rockstar engineer, so glad to have him here.
Thank you, Shrikant, for introducing our path to get to multi-tenant clusters. Now, let's continue the discussion on the risks and controls needed in multi-tenant Kubernetes clusters. We'll delve into the security challenges and solutions associated with shared compute in Kubernetes. Let's begin by exploring security risks in shared compute environments. In traditional single-tenant clusters, the boundaries of a services are well-defined. However, Kubernetes was not originally built for secure multi-tenancy. This lack of default isolation can lead to privilege escalation between tenants. For example, permissions via the control plane are not restricted to a single tenant namespace, and pods can be configured to access the nodes, allowing service owners or deployments to abuse this lack of isolation and escalate their privileges onto the node and other services running there. Another risk is the use of overly permissive identities. By default, Kubernetes uses the node identity for all services. All tenant-required permissions are needed to be given to the node. This does not follow the least privilege principle, as services will share each other's permissions to cloud resources. Unauthorized access is a significant risk in multi-tenant Kubernetes clusters. Developers often have broad access to their clusters by default. For example, developers may inadvertently or maliciously access services or logs belonging to other tenants. Allowing developers access to services owned by other tenants increases the risk of accidental or intentional changes that can impact the entire cluster. This unrestricted access can lead to unauthorized changes, deployments, or even service disruptions. To address all of these risks, we need robust security controls. Let's briefly overview these controls for each of the three areas. For privilege escalation, we proactively block known bad configurations that could lead to privilege escalation. We enforce policies for service placement, ensuring that services are scheduled on clusters based on their sensitivity and potential impact. Additionally, we monitor and patch disclosed vulnerabilities to minimize the risk of exploitation. For overly permissive identities, we implement per-service and component identities, ensuring that each service has its own permissions that only it needs to operate, following the principle of least privilege. For unauthorized access, we limit developers' access to only their service namespaces. Additionally, we restrict access to service logs, ensuring that each tenant has access to only their logs. Kubernetes, by design, does not provide strong isolation guarantees between pods running on the same node. This means that a compromised service pod could potentially access and manipulate other pods on the same node, even if they belong to different services running in different namespaces. To mitigate this risk, we employ a custom admission controller. For those who are not familiar, an admission controller is a Kubernetes mechanism that intercepts and validates requests to the Kubernetes API before they are persisted into the cluster. It allows us, as a production security team, to enforce security controls that apply to all Kubernetes deployments. In our case, we built policies into our admission controller based mostly on Kubernetes pod security standards. These are standards for best practices to secure deployments in Kubernetes. We chose controls from these standards that prevent known privilege escalation paths that we care about in multi-tenant clusters. For example, we restrict the use of privileged containers, which have access to all Linux capabilities, and prevent pods from using host namespaces, which could allow pods to access host resources. Both of these would break isolation between co-tenant services. By enforcing these standards, we can significantly reduce the risk of privilege escalation between services in our multi-tenant Kubernetes clusters. We occasionally encounter scenarios where service owners were used to quickly debugging their service by execing into their containers using pod exec. You security-minded folks will recognize this can be extremely risky, especially if there are containers with elevated privilege within a service namespace. To mitigate this risk, we implement a targeted approach that allows the necessary access while maintaining stringent security measures. Specifically, we limit pod exec exclusively to non-privileged service-owned containers, in addition to auditing all actions performed in production. This control ensures that any privileged system containers do not become a path to privilege escalation. Identities are a basic security concern. The use of overly permissive identities is a huge risk. As you may have run into, pods run with the broad access node identity, the default compute service account with editor role. Using this identity does not meet least privilege, especially when we start needing to grant additional permission for different services to run and access their data. To ensure least privilege identities, we use GKE Workload Identity Federation. This allows us to deploy pods with per-service identities, ensuring that each service has only the permission it needs to run. For instance, a friend service might have permission to access a friend's database, but the other services running alongside it will not be given permission to that same database. We have also ensured provisioning of identities per GKE components like nodes and our add-ons. For example, our auto-scaling add-on has its own identity that is not shared with the more privileged runtime security add-on. With Workload Identity Federation, identity access moved away from the node-level metadata server to the pod-level metadata server. Now that we have established our identity model, let's jump into how we think about access. As Shrikant mentioned, when we were reevaluating the security posture of Mesh, one of the things we wanted to address was the broad developer access to their clusters and deployments. In our multi-tenant environments, this problem and hardening access becomes a critical control we need. Our shared cluster platform would not be possible without it. In order to accomplish this control, we limit deployments and changes to production via a golden path. The golden path ensures that all changes are tracked and audited, providing a clear trail of who did what and when. We use GKE RBAC to ensure service owners' access is limited to specific non-mutating actions only in their namespace. We don't want out-of-band changes to production deployments. Now that we have covered access to deployments, let's cover access to the GKE control plane. They are on the internet by default, and we need to protect against external attacks and also follow GKE security best practices. At Snap, we implement the Beyond Corp Zero Trust access pattern, and we have our own auth proxy at the edge that provides context-aware secure access. We added support for GKE to that same proxy, and we enforce its usage using GKE's authorized networks. This security control is transparent to developers. Their experience in connecting via kubectl is unchanged. Our kubectl contexts are auto-generated to go through our auth proxies and also set the service namespace by default. So far, we have discussed controls to production. Let's talk about hardening the path to production. To ensure deployments come from the golden path, our CI/CD pipeline signs built images, and the admission controller we have validates those image signatures. This control ensures provenance from code commit to build to image. Only approved and verified code is deployed to our clusters, reducing the risk of malicious code being deployed. One of the challenges here was moving away from using mutable tags to immutable image digests, requiring us to update all our platform components to support digest. This cost trade-off was worth the security guarantees that come along with using immutable digests. It's not only about platform security, we also care about the isolation of our service logs. Service logs are emitted in shared cluster projects without per-tenant isolation. To address this, we configure GCP log sinks and buckets to route logs to service-owned GCP projects, ensuring per-tenant isolation. This means that each service logs are ingested directly to respective service-owned projects, preventing unauthorized access to logs from other service owners. This configuration of GCP log sinks and buckets all happens automatically when a service onboards to a shared cluster. Okay, so at this point, all our security controls give us isolation between services and secure the access to them. But for our team and other security stakeholders, multi-tenancy still felt like a pretty big risk. In order to further reduce fears around the shift in the security boundary, we had to go to the drawing board and think of how we want to co-locate services together on clusters by threat modeling attributes such as access to sensitive data, internet exposure, and service tier. This was a tough discussion as it was hard to align on the security benefits given the increase in complexity. In the end, to further control the blast radius of services sharing the same cluster, we evaluate co-tenancy policies at workload onboarding. These policies limit which services can be deployed along which other services and to which clusters based on their attributes. Okay, at this point, we felt our multi-tenant clusters are secure with all these controls and policies, but new kernel vulnerabilities could undermine our assumption around container isolations. Vulnerabilities could make it so that containers can break out of their container and escalate to the node. In order to mitigate against this, we enforce the use of auto-upgrading GKE node pools. We have the ability to upgrade the entire fleet at any given moment, and we have a pipeline for our on-call to get alerted of security bulletins as they are disclosed, ensuring that critical vulnerabilities are patched promptly. I hope this was an insightful journey through all our multi-tenant security controls. I'll now hand off to Shrikant for a recap and conclusion.
Thank you, Sagiv, for discussing effective controls to mitigate security risk in multi-tenant KTS. I hope so far things are making sense. We spoke about how we evolved from an App Engine environment to the service mesh to multi-tenant service mesh. And as you all know, having a demo for a backend infrastructure is going to be challenging and interesting. So we don't have a demo, but we have a 1D slide which kind of encapsulates that part. So if you see from the left-hand side, this is a typical developer workflow. Developers either access to the production environment through CI/CD. That's where the regular routine path goes through. And for each of the deployments, our admission controller that Sagiv spoke about runs through a set of security policies. One of the security policies is build attestation, where we ensure that each of the builds or each of the deployments going to our production have come from trusted CI systems. They have passed through a lot of CI checks, and those deployments are signed. If the deployments are not signed, then we enforce and basically block them. Another example of security policy is the check on the registry of the container images. So we only allow certain approved registries from where the container images can be pulled. And if this check fails, again, we basically block the deployment. And this is how we ensure that the production has integrity. Now, there will be some cases where developers would still need access to the production. And that is provided through namespace access, but it's limited. It's read-only access. We don't want anyone to mutate the production environments, mutate the deployments, but they still get access to, if they need to troubleshoot or basically look at some of the specifics of their pods or containers within the services. Now, so far we spoke about the part to the production. Now, if we look a little bit more deeper into the production environment, that's where our service mesh platform is. This is a slight difference from the earlier service mesh diagram that I showed. Over here, we have now multiple services. For example, users, friends, messaging, they're all running within a same shared GKE cluster. But for our isolation guarantees, we have different identities and different access control model now. The node identity is separate, and it gets least privileges based on the only thing that is needed for that node to run as a part of a GKE cluster. And each of the service has its own workload identity, scoped to the requirements of that particular service, where it can access its data or basically call other services. So that's where the workload identity comes into picture. So this way, we provide strong isolations between the services within the shared environment, as well as it's basically easy for the whole CI/CD flow to go through. As well, into the production, this slide does not cover, but we also have add-ons or other Kubernetes components. They even get their own workload identity. And generally, those add-ons, for example, runtime monitoring, they would be running with higher privileges. And we wanted to basically have or partition them off from the workload identity of the services, specific services running, and totally separate from the node identity. So this is how our, in short, our multi-tenant service mesh platform looks like today. Now, to recapture the backend services at Snap's story, as I said earlier, we started with App Engine, then we moved to Service Mesh, which was our single-tenant Kubernetes-based abstraction across multiple clouds, which provided the usual benefits of security, developer productivity, performance. And with multi-tenancy, now we introduce infrastructure optimization, where we could optimize on the on the cost, on the usage of the infrastructure, as well as reduce our management of hundreds and thousands of cluster, and also optimally use our compute infrastructure. We have started all the new services migrating to this platform. Given that there were so many of security controls that Sagiv mentioned in his session, we wanted to make sure that we validate all of those controls. They are working and they are providing a guarantee that we are assuming. We also had gone through a lot of red teaming exercise, simulating a lot of attacks either through CI/CD, running privileged containers into this shared environments, making sure that the security and the integrity of these shared environments are strong. Now, we'll talk about some of the challenges. As I said earlier, no large projects are completed without challenges. We had a lot of that we faced. I'll talk first about the organizational challenges and then the technical challenges. So most of you all agree software migrations are not easy. We always face unknowns. There could be outages that might happen, and there's a lot of times this idea about if something is working well, why do we even change or move? And within our space, we had 4 archetypes of services. The services running in legacy infrastructure, which was outside mesh, probably some of the services which were there for a long time at Snap. Services that were integrated into Snap infrastructure as part of a merger and acquisitions or M&As. And then services running in the legacy service mesh that I discussed before, which was our move from App Engine. And then new services which will directly be written for this multi-tenant platform. So there were a lot of different types of services that we had to consider while migration. At Snap, we took the approach of prioritizing the migration based on the tiering of services. And we tier the services based on different understanding of the services or how critical they are to the core of business continuity. So for example, tier -1 service would be like an API gateway service, which is very foundational to the infrastructure. Tier 0 or tier 1 services would be providing critical business functions, and they will be serving the core products for Snapchat. So we are thinking about, as we were thinking about this tiering of services, we felt that starting with tier 2+ services was an easy win because it had lesser business impact. So that's how we started, and we defaulted to this new platform for all the tier 2+ services. However, we realized that for us to onboard the higher tier 1 or tier 0 services, we needed to prove to the rest of the engineering teams the impact of this platform. And for that, they wouldn't migrate unless we show that there are other tier 0, tier 1 services running on this platform. And I think some of you, especially the infrastructure people, would kind of align with this kind of thought or this kind of pushback from the engineering teams. So we thought the best way we can do is dog food our own platform. So we picked the services that are owned by infrastructure and security, which fall into this tier 0, tier 1, and those are the services we started with. So that way we could prove that this platform is really strong and is basically doing what we had designed it to do and what we are basically proposing it about. The second challenge, organizational challenge, was changing the developer workflow. We were moving from no-touch production where you cannot mutate the production environments directly. Now, again, for developers in the room over here, you'll understand changing any workflow or any behaviors it's not super welcoming. Especially, there's a lot of pushback on security teams, infrastructure teams. So we did face that, and that's another thing to think of when you guys are going on this kind of journey, that we have to ensure that developers get an easy path of migration to basically do their work that is needed, which is making changes to the services that they own and follow the CI/CD path, and they can make the production or basically iterate on their changes. One thing we made sure for always along the path and getting all the feedback from our engineering teams is to ensure we provide correct break glass scenarios, which are easy to kind of enable for critical business needs. And I think this kind of measures, like providing break glass or providing easier path for developers, made it easy for us, or at least it was a little bit where we could start onboarding a lot of the services onto this platform. So another interesting organizational challenge that I would like to mention over here is generally when we start with such large projects, the MVPs take long, and the leadership needs to show patience before we see realized impact. And we also noticed that, so we had to always kind of keep on making it clear to the leadership that, yes, this is the platform that we are working on, show small incremental changes, but the realized impact is a little bit delayed. Now we'll move to some of the technical challenges. One of the things that we had in mind right from the beginning, and as mentioned, or I emphasized a few times about the multi-cloud, we wanted to avoid any leaky abstractions as we kind of design and implement this platform. So the services that we talk about, I mentioned about the architects of services, but the requirements of the services are also pretty bespoke. Some of the services need local VPC cache. Some service dependencies are configured in a way that it's not easy to change the identity of the service. And we had to ensure we do not break any of these services, and the platform is incorporated with backward compatibility. So another challenge was to enable different access patterns. We talk about operator access. There was network access for the services running in this platform. Accessing the control plane, Sagi mentioned about that, where we configured authorized network for GKey behind our authenticating proxy. Now, because we had this fleet of thousands of GKey clusters, first thing we had to have a service to kind of continuously sync all the authorized networks. But some of the systems which need direct access to the cluster, especially for deployments like CD system, we use Spinnaker, and we have our in-house build service as well. Those are heavy services, and if we have to configure them through our authenticated proxy, then that will have cascading effect, and we have to make sure that this proxy is able to support such a load. So we had to make a lot of those changes and understanding as we kind of roll out these different controls. The workload identity that we mentioned, again, we had to understand the KTS namespace scope and how basically it maps to the GCP project scoping and the IAM between the Google Cloud versus the Kubernetes mapping of the service accounts. So there were a lot of challenges along that path as well. And I would recommend, highly recommend that do prototype if you are going along this path. We mentioned about a lot of these different controls that we mentioned all along this path. Automating all of these controls and making sure that they are integrated well and they work in sync has a lot of complexities. And we were also looking at Google Cloud and AWS and building abstraction layer. There were a lot of specific subtle differences between this, which always increased the engineering costs and which always basically delayed a lot of deliverables that we had to, which we had planned for. So this is a concluding slide, and we'll have some of the time for question and answers later. But just to recap and take you all back through our journey, as I said, App Engine is where we started. Service Mesh platform was our first venture into abstracting out based on Kubernetes. Then today, most of the time, we spoke about the multi-tenant Service Mesh platform. And this is not done. As we start migrating more and more services to this, and as we basically are learning about a lot of challenges that still our development teams are facing with respect to this, One thing we realize is it's difficult to kind of keep on having a knowledge, institutional knowledge about Kubernetes, management of Kubernetes, and the cluster management for the development teams. A lot of times there is churn in development teams, and the knowledge has to be always kept up. So we are thinking about moving to this idea about managed services, where all of the nitty-gritties of Kubernetes and the infrastructure platform is abstracted out. All we want our development teams or engineering teams to write their code and use standardized mechanisms through CI/CD, through our internal portals, to reason about their services and go about making incremental changes. Other thing we are thinking in this managed services future is abstracting out container images from the development team as well. Having the container images as a packaging mechanism for softwares is been, I think, pioneered in the industry now. But the challenges comes with, again, heterogeneous based images, a lot of vulnerabilities that come into picture or into the production because of these different container images, and managing those, patching those is still a problem. So we want to abstract it out in a way that we should be able to, behind the scenes, update those as we need. As we all know, supply chain security is a big in the news nowadays, and we wanted to have some measures around that too. So the idea about decoupling the software dependencies from the rest of the software, and the ability to patch and update those dependencies outside the scope of general software development, I think that's one of the things that we want to move to, where we can keep our dependencies updated. We can patch them whenever there is a known vulnerability. So that way it's easier to keep the security of our production environments. And I don't know if you guys have been noticing, this is our managed services is kind of a full circle going back to how App Engine works. And but I think that's how we want to think about it, based on having much more control with respect to optimizing our infrastructure using Kubernetes, where we can even optimize our compute and even have the types of different computes that we can have, and an automated way to kind of manage this fleet. So I think that was our concluding slide. I will really appreciate if you all can provide feedback for this session. That will help us understand how we did, and then what we can do for the future sessions. So I really appreciate everyone's time here. Thank you for coming over.